Okay, so thank you all again for being here. I know it's been 3 weeks, so it's easy to lose momentum when you have this long a gap. And I know everybody's got the WASC going on, so there is a lot of things going on. So I appreciate that despite all of that, that you all still come and make it to this class. Okay, so I've turned on the recording, so you can type your name into the chat so that I have a record for your attendance so that you can continue to get data. We have 3 more classes for this year. So today and then next week, the 22nd, and then the week after on the 29th is going to be the last class. And then we'll resume in the fall. Okay, so welcome back, everybody. I hope you're doing well. I hope you've had a good few weeks. I want to review what we did last time because it's been a very long time since we talked about it, and we'll do some practice problems together. And then I'll want to do our new unit today, which is going to be to talk about sequences and series, which I know is part of the curriculum, at least for the 12th grade curriculum. Okay. So let me start by just doing a little bit of review about what we talked about last time, which was a while ago. So first I want to make sure my pen has enough battery. Oh yeah, good. My pen's good. Okay. Okay, so last time we talked about this exponential growth and decay. And we saw this was a simple equation and that it modeled lots and lots of different things. So this could model population, heating, cooling, radioactivity. Turns out it has a financial application as well. So we'll talk about all of that today. But the simple equation that we're using the whole time is this differential equation given by dy dx equals ky. And here, this k here is a constant. Okay? And the idea is this dy dx is the rate of change of y with respect to x. So really this x, we should really think of this as t. Let me write this as t. So this thing here represents a rate of change of y with respect to time. Okay, and what we're saying is that the rate of change, the rate of growth of y, is proportional to the value of y, right? So it's equal to a constant times the value of y, right? So this here is the value of y. Okay? And so a quantity that satisfies this differential equation, we call it either exponential growth or exponential decay. Exponential growth is when this constant is positive, and exponential decay is when the growth is negative. Okay, so if k is positive, for instance, that means that the amount that dy dt is positive. It increases with the amount of y. If k is negative, then dy dt is negative. It means that it decreases with the amount of y. And this constant k is sometimes called the relative growth rate. Okay, good. We got more people coming in now. Good. Everybody should be joining. Great. So this exponential growth decay is used to model lots of things. So it models population growth, radioactivity, compound interest, and heating and cooling via Newton's law, which we'll recall. And it turns out that the solutions to this equation, I'm going to, again, call my independent variable. I'm going to call it t instead of x. So it takes the form y equals c e to the kt. So it's a lot of letters. So let's, recall what all of these letters mean. So y is the quantity that you're interested in. So it might mean the amount of radioactive material or the amount of population or the amount of money in a bank account. It can mean lots of things. C here is a constant, arbitrary constant. K here is the relative growth rate from the original equation. T is time, and E is this number E. Remember, E is this specific number. E is roughly about 2.71828, etc. So this number, it's about 2.7. Okay. And so we know that for anything that's modeled by exponential growth or decay, the amount of stuff at time t is given by this expression. And then the difficulty in any problem is to try to figure out what is the correct value for k and what is the correct value for c. Once you know the values for k and for c, you have numbers that you can use for them. Then this is just an equation that lets you plug in t and get a value for y, which is what you want. Okay. So this is the idea for these exponential growth and decay problems. And let me just spell it out a little bit more explicitly. So when you're solving an exponential growth and decay problem, you know that the equation giving the desired quantity in terms of time is always y equals c e to the kt. This is just what we wrote on the last slide. We have some constant c and some constant k. And the key to the problem is always, 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 what you need to know is you need to figure out what is c and what is k. And once you know this, once you know what c and k are, then y and t are related by an equation, and you can solve for one in terms of the other. Now, what's hard about these problems is that there are two things that you need to figure out. You need to figure out c, and you need to figure out k. Okay, and in order to figure out those two pieces of information, you're always going to need two pieces of information in the problem. So anytime you have a problem like this, you're always going to be given at least two pieces of information, because that's going to give you two equations, one of which will let you solve for c, and the other of which will let you solve for k. Okay. Okay. So any questions? Of course, we're not actually doing anything, but this is the setup. You have something with exponential growth and decay, and the solution is based on this equation, but you need to know what c is and you need to know what k is, and the different values of c and k will be different depending on the problem, okay, depending on what you're trying to model. Okay, so let's try an example. So this is the first homework exercise. So strontium-90, this is a radioactive isotope. It has a half-life of 28 days, okay? A sample has a mass of 50 milligrams initially, and then we want to find a formula for the mass remaining after t days. And then the question is, how long does it take for the sample to decay from 50 milligrams down to 2 milligrams? And maybe I should recall what a half-life is. Recall, half-life equals the amount of time for half the radioactive material to decay. Okay. So this is what the definition of half-life means. It's the amount of time for half the radioactive material to decay. So we're always going to always start with the general equation, which is y equals c e to the kt. And here y equals the amount of substance and t equals time in days, right? Because this is about t, it says t days, right? So the time is measured in days. Okay, so what are our two pieces of information that we're going to be able to use to solve, right? Well, the first piece of information is that the sample has a mass of 50 milligrams initially. Usually you're given something at time 0. That's what initially means. It means t equals 0. Okay, so what this tells us is that, information piece 1, so the information piece 1 says that if t equals 0, y equals 50, right? So this is the amount of substance in milligrams. Okay, so if t is equal to 0, y equals 50, because that's what it says. It has 50 milligrams initially. So we can plug that in. This gives us that 50 is equal to c times e to the k times 0. But that's the same thing as c times e to the 0, which is the same thing as c. So this tells us that c is equal to 50. Right, this is the first piece of information, is that at time 0, we have 50 milligrams. So the second piece of information that we have here is that the half-life is 28 days. So that means if we start with 50 milligrams, it's going to take 28 days for half of that to be gone. right? So information piece two, says what? Well, it says if t equals 28, right, 28 days later, then y equals half of what we started with. So that's y equals 25. And so what does that tell us? Again, we have our equation, y equals c e to the kt. So we plug in 25 for y equals c. Well, we know what c is. C is 50 times e to the k times 28, which implies we divide both sides by 50. That tells us that 1/2 equals e to the k times 28. And then, hi, Rosh, how are you? So then remember, we want to solve for k. So in order to do that, we have to take the natural logarithm of both sides. So that tells us that ln of 1/2 is equal to k times 28. And that tells us that ln of 1/2 divided by 28 equals k. And now I can use a calculator to figure out what that is. So if I look at ln of 1/2 divided by 28, that looks like k should be negative 0.0248. Okay, and that's how we round it well enough. Okay, so k is 0.0248. So now we have all of the information. So now let's actually answer the question. So what does the question ask? Need a little bit of extra space here. So the question says, find the formula for the mass remaining after t days. So after t days, you have, well, that's just asking you what y is. So it's c e to the kt, but we know what c is, and now we know what k is. This comes from the second piece of information. And so we get 50 times e to the minus 0.0248 t milligrams of substance of strontium 90. Okay, so that's what it is after t days. And then we want to know how long does it take for the sample to decay to 2 milligrams? So we solve 2 equals 50 times e to the negative 0.0248 t. Well, that's to say we can divide both sides by 50, so that's 1 over 25, same as 2 divided by 50, equals e to the minus 0.0248 t. Again, we have to take ln of both sides, so we get ln of 1 over 25 equals negative 0.0248 t. And then lastly, we get that ln of 1/25 divided by negative 0.0248 equals t. And let me again put this into a calculator so I know what this is. So if I look at ln of 1/25 and I divide by minus 0.0248, that looks like this gives us that t is equal to roughly 130 days. So I apologize for a bit of the clutter on the slide. I wanted to get everything. I wanted to get everything on one slide so we could see everything. But the point is, the way that you do this problem is always the same. You know the solution is y equals c e to the kt. You need to use the pieces of information in order to determine what is c and what is k. Once you know what c is and what k is, then you have your general formula. The amount of substance is 50 times e to the minus 0.0248 t. And then you can answer any question you want about how much is left after a certain time. So if it says, how long does it take the sample to decay to 2 milligrams? We want to know, when will this expression be equal to 2? So we have to solve for t. Right? 2 milligrams should be equal to this much. And it turns out that t is 130 days. And that kind of makes sense, right? Because every 28 days, you lose half. So after 28 days, you're down to 25 milligrams. After 56 days, you're down to about 12 milligrams. After 84 days, you're down to about 6 milligrams. And then after, another 28 days, so after 112 days, you're down to about 3 milligrams. So it makes sense that to get down to 2 milligrams would be about 130 days. Okay, so this is a realistic looking solution. Okay. Any questions about this problem?
Hello, sir.
Yeah, Rush?
Yeah, the 28 days is not included, right? Because somehow just joining the class as problem.
Oh, sorry. Well, I mean, the 28 days is part of what's given to you, right?
Okay,
So
okay.
it's part of the substance. If this was a different radioactive substance, it would have a different half-life, right? So 28 days, I just looked this up. So 28 days is the half-life of strontium-90.
Okay.
So the
Yeah,
28 days shows up here in the information piece too, which is saying that 28 days later, if T is equal to 28, then you've lost half the substance. So that means you have only 25 milligrams instead of 50. So that's where we're using this 28 is to punch in here and solve for K.
yes, yeah, there.
Yes, Prince, hi.
Yeah, thank you. I have a concern here where we said 2 is equal to 50 times e raised to the negative 0.248 to the t.
Right.
Okay, I have a concern there. Okay, how we got the 1 over 25th?
I divided both sides by 50 here. So dividing the right side by 50, the 50 goes away, and dividing the left side by 50 is 2 divided by 50, which is the same
Okay.
as 1 divided by 25.
Thank you. Thank you. It's understood.
Okay.
Sorry, Bernard.
Great. No problem. Yeah, if I had more space, I would have written out the extra step, but I didn't have enough space on the slide.
Yeah, it's understood. Thank you. Thank
Okay,
you.
good.
Just sorry.
All right, other questions? Okay. All right, so we'll do a few more examples so you can recall this. Okay, so I want to recall another physics application of this. So this is Newton's law of heating and cooling. We talked about this last time. So if we have the temperature of an object at time t, we have uppercase T and lowercase t. Lowercase t stands for time, uppercase T stands for temperature. And if T sub S is the surrounding temperature, so in the example problem, there's going to be a bowl of soup and it's going to be outside. So TS is the temperature outside, that's S for surroundings, and then T is the temperature of the bowl of soup. And what Newton's law of heating and cooling says is that there's a constant T so that dt, so this is, again, remember, it's a rate of change of T with respect to time, that this is equal to some constant times the difference between the temperature of the object and the temperature of the surroundings. And what we did last time is if we make a change of variables, if we let y be not just the temperature, but the difference between the temperature and the surroundings, then since y is just t minus a constant, the derivative of y is the same thing as the derivative of t, right? This extra constant doesn't do anything when you take the derivative. So we have that the derivative of y with respect to time is the same as the derivative of the temperature with respect to time. So instead of this over here, we can write dy dt, and then since y is t minus ts, we can write y over here. So right, really this thing is just y. So when we make this change of variables and we rewrite the equation, it looks like the exact same exponential growth and decay equation that we had before. Okay, the only difference is that this y now doesn't represent temperature. It represents the difference between the temperature of the substance and the temperature of the surroundings. Okay, and this is just left over from last time, but we showed last time that k is always going to be a negative number here. And that's because if your object is hotter than the surroundings, that means y is positive. If I leave out a bowl of soup and the soup is hotter than the temperature outside, then what's going to happen to the soup? It's going to cool down, right? Or if I leave a block of ice outside and the ice is colder than the temperature outside, then what's the ice going to do? It's going to melt. It's going to warm up, right? So the rate of change is always in the opposite direction of T minus Ts, right? If T is bigger than Ts, that means this is positive, but it's going to cool down, which means the rate of change is negative. If T is smaller than Ts, meaning the object is colder than the outside, then this quantity is negative, but that means the object is going to warm up. So this is going to be positive. So in both cases, the sign of dt is different than the sign of T minus Ts. And so to turn one sign into the other, this constant K over here has to be negative that you're going to multiply it by. Okay, so K is going to have to be negative here. All right, so let's look at this again, how we do this in a problem, okay? So a bowl of hot soup is taken off the stove at a temperature of 130 degrees Fahrenheit. The temperature outside is 80 degrees Fahrenheit. 2 minutes later, the temperature of the soup is 110 degrees Fahrenheit. And the question is, how long will it take the soup to cool to 100 degrees Fahrenheit? Okay, it takes 2 minutes to go to 110. So that's cooling 20 degrees. So if you don't know Newton's law of heating and cooling, you might say, well, if it takes 2 minutes to cool 20 degrees, then it should take 3 minutes to cool 30 degrees. That would presuppose a linear relation between time and temperature. But what we're going to see is that's not actually right. It's going to take more than 2 minutes for this. It's going to take more than 3 minutes for the soup to cool to 100 degrees Fahrenheit. So the way we set this up is we always have, again, y is equal to c e to the kt, where here t equals time in minutes, and y equals soup temperature minus the outside temperature. So the soup temperature minus 80 in degrees Fahrenheit. Okay. Okay, so again, we need two pieces of information. First piece of information. What's the first piece of information? Well, it says it is taken off the stove at a temperature of 130 degrees Fahrenheit. So usually you're going to be told how we start. So we start, it's 130 degrees Fahrenheit. So this says when t equals 0, y is equal to 130 minus 80, which is equal to 50, right? Is that okay?
So yeah, I have a question, sir.
Mm-hmm.
Why would get a t? Why would get 0? Why would make t to be 0? Why is that
T is
constant
0
or
means when you start, right? So
Okay,
t is the time, the amount of time that's elapsed. So the beginning time is always t equals 0.
Okay, so it's t. Okay.
Right. So what does this tell us as far as equations go? Remember, our equation is always y equals c e to the kt. So this tells us, well, y is 50. That's equal to c times e to the k. Well, t is times 0, right? C e to the k 0. And that tells us that 50 is equal to c e to the 0, because k times 0 is 0. But e to the 0 is just 1, so this tells us that 50 equals c. If you have two different temperatures like Celsius and Fahrenheit, it's fine. You just want to convert it all to one temperature and work the whole problem in that one temperature. So there's no difference between Celsius and Fahrenheit as far as the rule goes, but you need to make sure that all of the information in your problem is in terms of the same scale. So if you like doing it in Fahrenheit, then do the whole thing in Fahrenheit. Convert everything to Fahrenheit before you start. If you like Celsius, then convert everything to Celsius before you start. The equation is the same no matter what. Makes no difference.
So thank you, sir. Okay, another so that means Prince. That means whenever it's in the same unit, it's possible to be solved, but different unit, you have to carry on conversion.
Exactly. You
right?
can't deal with
Okay.
Fahrenheit and Celsius together because this equation assumes that everything is in the same units.
Okay. So can they work also with Kelvin? Can we take Kelvin only as well?
Yeah, Kelvin is fine. Kelvin's
Okay.
completely fine. Yeah.
Okay.
Yeah, Kelvin's completely fine. Any units are fine as long as you use the same unit for everything.
Okay. Okay. Thank you.
In fact, right, I mean, if you do Celsius versus Kelvin, your Y is the temperature minus the temperature outside. If you change Celsius to Kelvin, all that's going to do is it's going to add the same number to the soup temperature and to the temperature outside. So the difference is going to be the same. It's not going to make any difference when you subtract.
Okay. Okay.
Yeah,
Yeah.
right.
Sorry.
Yeah. So, right, this 50 is going to be the same whether we're dealing, well, I mean, in this case, it's Fahrenheit, but if you converted it to Celsius, it would be the same as if you converted it to Kelvin.
All right. Thank you so much.
Good. Okay. Other questions? Okay, so what's our second piece of information here? Well, we said that 2 minutes later, the temperature of the soup is 110 degrees Fahrenheit. It's fine because actually, so if on, okay, so let me answer this question. It says, what if on a test they're different and one student takes Celsius and the other student takes Fahrenheit? The good news is this question is asking about time. And if you do the problem in Celsius and somebody else does the problem in Fahrenheit, you're going to end up getting the same amount of time. You're going to get the same answer in minutes. So it doesn't matter whether you do it in Fahrenheit or in Celsius because it's asking about something real. This is asking about a bowl of soup and how long it takes to cool to a given temperature. So whether you call that temperature Fahrenheit or Celsius, it doesn't affect how long it takes the soup to get cold. So you can do it in either unit and you should get the same answer. Okay, so James has about 3.64, which I assume is right. But let's work this out. Okay, so second piece of information says 2 minutes later. So when t equals 2, the soup is 110. So that means y has to be 110 minus 80, which is equal to 30. So that's going to tell us that 30 is equal to 50 times e to the k2. Right? Because this is over here, this is our y, and this is our t. Oh, sorry, I didn't mean to write that. Sorry. This is our y, this is our t, and this is our c. We already solved for c. Okay, so what does this mean? If we divide both sides by 50, we get 30 over 50 equals e to the 2k. Again, take ln of both sides. So ln of 30 over 50 is equal to 2k. And this is going to tell us that ln of 30 over 50 divided by 2 is equal to k. And we can then solve for k. So let's solve for k. So ln of 30 over 50 divided by 2 is going to give us k equals about negative 0.255. No, the question could ask for anything. So if the question asks for a temperature, then if one student does it in Fahrenheit, then the question should ask, what is the temperature in degrees Fahrenheit? Or what is the temperature in degrees Celsius? So if the question asks for a temperature, then you should do it in the units that the question asks for. Yeah. But this question asks for time. We'll have other questions that ask for things other than time. Okay, so in this case, our k is negative 0.255. Okay. Okay. Okay, so now we know what the equation looks like. We've solved for k and we've solved for c, right? So we have that y is equal to 50 times e to the minus 0.255k, right? This is our c, and this is our k. Okay, right? And so now what does the actual question say? It says, how long will it take the soup to cool to 100 degrees Fahrenheit? So what we want is to solve for t. Oh, sorry, this shouldn't say k. This should be t. That is k, 0.255t. So we want is to solve for t when y is equal to, well, 100 degrees Fahrenheit. So we have to take 100 minus 80 minus the outside temperature, which is 20. Right? So we get 20 equals 50 times e to the minus 0.255t. That tells us that 20 over 50 equals e to the minus 0.255t. Again, ln of both sides, ln of 20 over 50 equals minus 0.255t. And that tells us that t equals ln of 20 over 50 divided by negative 0.255. And what is this? Again, it should be, I assume, what James did, but let me just double check this. So ln of 20 over 50 divided by minus 0.255. I'm getting a slightly different answer. I'm getting about 3.59. Getting that this is about 3.59 minutes. Okay, so I'm getting a slightly different answer, but I think this is right. Okay. So we see that it takes a little bit longer, right? In 2 minutes, it cools off 20 degrees. But then to cool off the next 10 degrees, it's not good enough to just take 1 minute. It actually needs to take a little longer than 1 minute. You need an extra 1.59 minutes past the 2 minutes. And that's because as the soup gets closer and closer to the outside temperature, it cools off slower and slower. Okay, and this is, if you have something that's much hotter than it is outside, it's going to steam, it's going to smoke, it's going to cool very quickly. But once it's only a little hotter than it is outside, then the cooling starts to slow down. This is, the nature of how objects cool. So that next 10 degrees takes longer than the first 10 degrees. And the 10 degrees after that will take even longer. If we wanted to know how long it would take to cool to 90 degrees Fahrenheit, my guess is that it would be more than another 1.59 minutes. Probably would be 2 or 3 more minutes just to get it down to 90 degrees Fahrenheit. So it's a good question to do. You can ask the same question for 90, in which case you just have to plug in 90 instead of 100 here and solve for the amount of time. So that's a good exercise to do if you want to do it on your own. Okay, but yes, James.
Yeah, a little confused of the equation given for y c e raised to the constant. Is that the constant k?
Yeah, k is constant.
So how can we know that constant in the formula? I really don't understand how we get that.
So we don't know what we always just know that the equation looks like this. But the constant's going to depend on the substance. So it depends on what kind of soup you have, right? If it's like a really thick soup then versus a watery soup, then the constant might be higher or lower. So the only way you can know what the constant is by using the information that you're given in the problem. So here we have this second piece of information, which is that 2 minutes later, the soup cools to 110 degrees, right? So what that tells us is that in this equation, at time 2, t equals 2, the temperature is 110 degrees, which means that y is 110 minus 80, which is 30 degrees. So when t equals 2, y equals 30. And then what we can do is we can plug those values into this equation, and that can help us solve for k. So we know that y is c e to the kt. We already proved that c was 50.
In class, come in 1 minute.
Sorry, okay. Right, so we already knew that c is 50. So now we say, well, when t is equal to 2, y has to be equal to 30. And now you have this whole equation where the only variable is k. And once you know that the only variable is k, then you can solve for k. And this is exactly what we did. So we solved for k over here, and we got that k was equal to minus 0.255. So the only reason we can solve for k is because we know a value for t and a value for y and a value for c. So k is the last variable.
So, like, hello, boss?
Yep. Mm-hmm.
Yeah, so like I saw the pattern when you're solving the piece-bar function, when t was zero, you know that zero times anything is zero, so you didn't care for k in solving. But when we have t get value, now we solve k. So now the k value, are we going to put it back in the formula for the third piece-bar function, right?
Exactly. And that's exactly what we do here. So the point is that the two pieces of information are what let us determine C and K. And once we've determined C and K, now instead of just writing this general equation, which governs all exponential decay or growth, now we have a specific equation that specifically says this is how this soup cools. And the way this soup cools is with a C equals 50 and K equals minus 0.255. So preliminary steps are you figure out C and K. And then the next step when you're actually solving the problem is you use those values of C and K to relate Y and T. So it's a little confusing because there's 4 different variables floating around. But what you have to do is first determine C and K and then use that to relate Y and T. Is that clear?
100%, 100%.
Okay. James, is that okay?
I understand. Thank you, Dr. Abbas.
Okay, great.
Yeah, thank you.
Okay. Other questions?
I understand. Thank you.
Okay, good. No, any questions from anybody else? Okay. All right. Let's do one more. So one more radioactive question. So a sample of tritium-3. So tritium, by the way, that's hydrogen. So tritium, for the chemists among you, this is hydrogen-3. Okay, so it's a hydrogen with 1 proton and 2 neutrons in the nucleus. Highly, highly radioactive. Okay. So not something that you find a lot of in nature. So a sample of this decayed to 94.5% of its original mass after 1 year. So the question is, what is its half-life, and how long will it take the sample to decay to 20% of its original mass? Okay, so this looks a little bit different, but I claim we can do this exactly the same way as we do all of the other questions. So always we have that the equation is y equals c e to the kt. Okay? So what makes this a little bit harder is that it looks like there's only one piece of information. It looks like all that we have is that it decayed to 94.5% of its original mass after 1 year. Okay? But it turns out this actually is 2 pieces of information. It's just hidden. What's the second piece? So what you can say is, I never told you how big the sample is, right? But what's also clear is that it doesn't matter how big the sample is, right? The half-life of a substance doesn't depend on how big the sample is. It just depends on what the substance is. So tritium-3 has a half-life. And it doesn't matter whether it's, 100 grams of tritium-3 or 5,000 grams of tritium-3. It makes no difference. The half-life is the same. The half-life just depends on the substance. So we may as well assume we can make this sample whatever size we want. So it's okay. I'm going to say that the sample size doesn't matter. Okay, so we may as well assume, let's just assume it's something simple. Let's assume it's, 1 gram. And so assume our sample size is 1 gram, just to make it simple. You can assume anything you want. You're going to get the same answer no matter what. Okay, so what this tells us is the first piece of information. This tells us that at t equals 0, y equals 1. Okay, at the original sample size is 1 gram. Okay, so again, this tells us that 1 equals c times e to the k 0, which is the same as 1 equals c e to the k, which is now we take, which is the same as 1 over c equals, 1 equals c e to the 0. Sorry. And that is the same thing. E to the 0 is 1. That's the same thing as 1 equals c, right? So c in this case is just equal to 1. And now we can use the second piece of information, which is after 1 year, it decayed to 94.5%. This is the decay equation, exactly. So this says that at t equals 0, y it shouldn't be 1 anymore. It should only be 94.5% of 1. So it should be 0.945, right? That's what 94.5% of 1 is. Sorry, not t equals 0. At t equals 1, y should be equal to this. So what does that tell us? That tells us 0.945 equals, well, c is just 1 times e to the k t. Well, t in this case is 1 also. So this will be a pretty easy equation. So 0.945 equals e to the k. And that tells us that k is equal to ln of 0.945. And that is equal to about, so ln of 0.945 is about negative 0.0, sorry, negative 0.0566. Okay, I'll leave 3 decimal places because that's how much we have. Okay. Okay, so this is what we have. Okay, so this is our k. This is our k, is negative 0.0566. So now we know what our equation is. So our equation is y equals, well, c is just 1. So it's just e to the negative 0.0566 t. So now the question is, what is the half-life? Right, so natural logarithm both sides, but we need to solve this. So what is the half-life? Well, if we started with 1 gram, then the half-life is asking how long does it take the sample to decay to half a gram, right? That's what the half-life would be. How long does it take to go to half a gram? So the question asks, how long to decay to 0.5 grams? What that means is y equals 0.5, right? That's what this is asking. So what do we get? We have that 0.5 equals e to the minus 0.0566 t. As James says, take the natural logarithm of both sides. So you get ln of 0.5 equals negative 0.0566 t. And so ln of 0.5 divided by negative 0.0566 is equal to t. And this tells us, let me write this down. So what is it? ln of 0.5 divided by minus 0.0566. So this tells us that t is equal to about 12.25 years. Okay, so the half-life is pretty long. Yeah, so again, our decimals might be a little off depending on how many places we round to, but 12.25 years, 12.16 years, it's all basically the same. Okay, so 1 year, this kind of makes sense, right? Because in 1 year, it loses only about 5% of its mass. So it's going to take a long time to lose 50% of its mass. Turns out that it actually takes 12.25 years. So this is really the first question. And now the second question is the same thing, but it says, how long will it take for the sample to decay to 20% of its mass? So the second question is the same thing. It's how long to decay to not 0.5 grams, but now 0.2 grams. So y equals 0.2, right? How long to decay to 20% of its mass? So we just do the same thing, but we just use a 0.2 instead of a 0.5 here.
Hello,
Right?
sir.
Yes, hello, Rush.
Yeah, are we assuming the masses?
We're assuming that the mass is 1 gram, But
Yeah, from
that's nowhere in the problem. The point is that it doesn't matter what the mass is because these questions don't depend on the original mass. The half-life is the same no matter what. So we may as well just make an assumption on the mass that's simple. So the easiest thing to do is to just assume that it's 1 gram. It doesn't matter what you assume, you'll always get the same answer for any of these times because these questions don't depend on how much substance there is. It just depends on, the half-life doesn't depend on how much there is. It's just a property of the substance. So tritium-3 has a half-life no matter how much of it you have.
okay. So the mass is
Sorry?
I think we
Rash?
just assume the mass is we just assume about it, right?
Exactly.
Yes.
So that's what I mean here when I say the sample size doesn't matter, so you may as well assume it's 1 gram, and this is just for simplicity.
After 1 gram, we assume like something like 0.5 gram too on the next step.
Right. Well, this is what we want to know the half-life. So if we start with 1 gram, we want to know how long does it take to become 0.5 grams. That's the half-life. And now the second question says, how much does it take to go down to 20% of the original mass? So that would be 0.2 grams. So let's solve this. 0.2 equals e to the minus 0.0566 t. So again, so ln of 0.2 equals minus 0.0566 t. That tells us that ln of 0.2 divided by minus 0.0566 equals t. And t, which I'm assuming is going to be a lot longer than 12.25 years. Let's see what happens. Yeah, so this turns out to be about 28.44 years. Right, so this answer makes sense, right? It's going to take much longer to decay down to 20% than it would take to decay to 50%. Okay. So, and it takes, the more that decays, the slower the decay becomes. That's exactly what exponential decay is. The less you have, the slower it is. So you lose 50% of the mass in the first 12 years, then it takes another 16 years just to lose another 30% of the mass. So that decay is definitely slower than how it started. We're not just assuming 0.2 grams. That's part of the question. The question says, how long does it take to get down to 0.2 grams? Right? The assumption is that 1 gram to start. So assume it's 1 gram, I'll say to start. Okay. And then if we're starting with 1 gram, it's asking how long does it take to get to 20%? So that's saying how long does it take to get to 0.2 grams? That's 20% of 1 gram, right? So that's what we need to solve for. The only assumption we're making is that we start with 1 gram. Everything else follows from that assumption. We don't have any freedom once we've made this 1 gram assumption. Then we just have to do what the question asks. It asks for half-life. That means how long to get down to 0.5 grams. It asks for 20%. That means how long to get down to 0.2 grams. Yeah, we're saying divide the 20% by 100. Yeah, because we're looking at what is 20% of 1 gram. That's what we're looking at.
Roberts?
Yeah, James. Well, let me take the question in the chat. 0.2 is not the change in time. 0.2 is just 20% of 1 gram. So we're just saying 0.2 is just here because we want to know how long it takes for the sample to decay to 0.2 grams. That's what the question is asking. 20% means 0.2 grams. If we assume that we started with 1 gram. Yeah, James Caselli, question?
Yes. Why not want to explain this? Because if 94% of the original mass can be decayed within 1 year, then why is it that it would take longer time for half of it to be decayed?
Well, I mean, no, 95.4% isn't what decayed. It decayed to 94.5%. So it only lost 5.5% after 1 year. So it's not that 94.5 decayed, it's that 94.5 was left after 1 year.
Okay. Okay, I understand. That's
Right.
right.
Yeah, yeah, yeah. So decay, yeah, it's this word too right here. Yeah. Yeah, no, that's a good question because if it lost 94.5 after 1 year, then these answers wouldn't make any sense. The half-life would be much shorter. But it actually only lost 5.5% after 1 year. And what was left was 94.5%. All right. Any other questions? Okay. So let me do one more application of this. So I want to talk about compound interest. Okay, so suppose you have a deposit of size D and it's placed in a bank paying an interest rate R. And interest rates are usually given in percent per year. So the question is, how much will be in the bank account after T years? And the answer is, this depends on, a technical thing which is called how often the interest is compounded. So in the most basic situation, the interest is compounded once per year, okay, which means that, let's say it's 5% interest to be simple. You put in $100, a year later, you get $105 because you're getting 5% interest. Okay, so if it's compounded once per year, then the amount is going to be your original deposit. This is D, this is original, times 1 plus R to the T, right? Because because what it's saying, so earning interest, earning an interest 5% interest means that we take R to be 0.05 to be 5%, and then each year, what does it mean to earn 5% interest? It means you have to multiply by 1.05. So each year you multiply the amount by 1 plus 0.05, which is 1.05. Okay, that's what it means to earn 5% interest. It means you multiply by, 1, which is what you start with, and then another 0.05. That's your interest. That's the 5% interest. Okay, and if you do that over T years, so if you do that over 10 years, then you're going to multiply by this 1.05 10 times. So we multiply it by, 1 plus R to the 10. Okay. So this is what happens when you have bank account interest that's compounded once per year, or if you owe a loan with interest, same type of thing. Okay. So now the question is, what if it is compounded n times per year? So what does this mean? Let me do this in the form of an example. So let's say that R is equal to 6% or 0.06, and say it's compounded 3 times per year. So what does it mean for it to be compounded 3 times per year? It means that you don't earn 6% interest at the end of the year, but instead you earn 2% interest a third of the way through the year, and then another 2% interest another third of the way through the year, and then the last 2% interest at the end of the year. So this is, 2% 3 times during the year. Okay. That's what it means. So you take the full interest rate and you split it up into 2% 3 times instead of 6% all at once. So then what do you have? So after 1 year, well, you have your original deposit, and then you're getting 2% interest 3 times. So it's D times 1.02 times 1.02 times 1.02. Or in other words, D times 1.02 cubed. Whereas this is, first interest payment. And then this is the second interest payment. And this is the third interest payment. Okay, each time you're getting multiplied by 1.02. So it turns out that after 1 year, since it's 3 times a year, you get d times 1.02 cubed, and that's actually a little bit more than 1.06. So 1.02 cubed, this is roughly equal to d times 1.0612. Okay, so it's a little bit more. So you're effectively getting 6.12% interest instead of just 6% interest every year. Okay. And this is what happens after 1 year. And so in general, well, if your interest is compounded n times a year, well, you get r over n in interest n times per year. So after 1 year, what do you have? You have your original deposit D. N times per year, you're getting an interest rate of r divided by n, right? You're splitting up your annual interest into n times per year. So that's going to be 1 plus r over n. And then that happens n times. So this is what you get, right? This example was the case where r was 6% and n was 3. So it's 1 plus 0.06 over 3, it's 0.02, and then raised to the 3. That was exactly this example. But in general, you get r over n in interest n times per year. Right, so in 3 years, yeah, if you started with 1,000, then you'd end up with 1156.6. So you have this. That's after 1 year, and in general, after t years, you have d times 1 plus r over n raised to the n, and then all of this raised to the t, because you're doing it t times. Or in other words, d times 1 plus r over n raised to the nt. Okay. So this is the formula for compound interest. So there's 3 letters, right? R is the interest rate. N is the number of times per year that it's compounded. And T is the number of years. Miata, let me just check to see if your answer is right. So Miata, I got for that example, after 3 years, I got an answer of $1,195, not $1,156. It should be, 1,000 times 1.02 raised to the 9th. Because in that case, you have r equals 0.06, n equals 3, and t equals 3. Okay. But this is the general formula. Okay, so yeah, if you have your interest compounded n times per year at an interest rate r, and for t years, and d is your original deposit, then it all goes together into this equation. Okay, so I'm going to write this on the next page. Right, so we've seen that if the interest rate is compounded n times per year, the amount of money in the account after t years is given by this. So let me label what everything is. This is the initial deposit. Okay, this is the annual interest rate. This n here is the number of times compounded per year. And this t over here is the number of years. Okay. So that's what all of these different letters mean. We've got 4 different letters that go into this formula. Okay, any questions about this formula? Okay, so now what banks actually do is they generally compound your interest daily. So 365 times a year, which is more or less the same as compounding it instantaneously. What does instantaneously compound? It means instead of just compounding your interest once a year or 3 times a year, It means they compounded infinity times per year. What does that even mean? How can you do something infinity times per year? Well, calculus tells us how to do this. So when banks do instantaneously, what they actually do is you take the limit of this quantity as n goes to infinity, right? That's what a limit tells you, right? If you go infinitely many times per year, that's taking the limit of this formula as n goes to infinity. Okay, and then in reality, this is what's actually done, right? So in reality, most banks actually compound daily equals 365 times per year, which is effectively instantaneously. Very little time is passing in between compounding of interest. So this is effectively instantaneously. Okay, so let's see what happens. So we need to calculate this limit. And this is a little bit tricky, especially since there's no numbers involved. It's all letters. So I'm just going to rewrite this as following. This is the limit as n goes to infinity of d times, so here's what I'm going to do. I'm going to write this as 1 plus r over n, and then instead of nt, I'm going to write n over r times rt. Right? All that I did was rewrite nt here as n over r times rt, right? It's the same thing as nt, right? I'm just rewriting it like this because we'll see. So n over r times rt. So now what I'm going to do is I'm going to let x be equal to n over r. I'm just going to make a change of variables. I'm just going to introduce a new variable. So then what do I get? This is the limit as n goes to infinity of d times 1 plus, well, r over n is the reciprocal of n over r, right? So it's the reciprocal of x. So that's actually, let me say this limit. So that's the reciprocal of x. So that should be 1 over x. And what do I get up here? Well, I have x is n over r, so that's just x. And then here I have rt. So x rt. And then if n is going to infinity, well, n's in the numerator. So if n is going to infinity, that means that x is going to infinity also. So I can write this as the limit as x goes to infinity of this quantity. So all I did here was make a substitution. I substituted x equals n over r, and now I have a expression that no longer involves n, right? I'm just writing this as 1 plus 1 over x, xrt. Now I'm going to do something that should not be controversial. I'm going to say this is d 1 plus 1 over x raised to the x, and then that whole thing raised to the rt. Right? All I'm doing here is using the laws of exponents to say instead of raising to the xrt, I'm going to first raise to the x, and then I'm going to raise to the rt. And now I'm just going to pull out a d, because the d is just a constant. So d times the limit as x goes to infinity of 1 plus 1 over x to the x, all of this raised to the rt. Okay, now here's where the magic happens. So does anybody recognize this limit? So the limit as x goes to infinity of 1 plus 1 over x to the x. This is how we defined a certain number this semester. So if you go back to a couple of months ago, you may not remember this limit here is exactly e. This is how we define the number e. This limit as x goes to infinity of 1 plus 1 over x to the x is how we define the number e. We actually showed that this worked by using L'Hopital's rule. So what happens is that this actually gets much simpler. This just becomes d times e to the rt. And that's the final formula. Okay, so if you compound your interest rate instantaneously, then the amount of money that you have after t years is just your initial deposit times e to the rt, where d and r are just the same things. D is the initial deposit, r is the interest rate, and then t is the amount of time. Okay, so it turns out that when you compound your interest instantaneously, you actually get a formula that's much simpler than the many times per year compounding. So this final formula that you get is just d times e to the RT. So if you know your interest rate, you know what you start with, then you know what happens after t years. And maybe that was e to the what's it, 1 point.
That works.
Yes.
So like the two formulas, what are the differences? Because one is let's say 3 is the 5 times, which is for n, and the next formula is it goes to infinitive.
Right. So
So
then there's going to be very little difference in reality between taking n equals 365 and n equals infinity here. The amount of money is going to be almost exactly the same. So, but the point is that this is much easier to calculate than calculating with 365 and this formula. So when you take n to go to infinity, the point is practically it makes almost no difference. It's going to be the exact same amount of money. But in terms of computation, this is actually a much simpler formula to use.
hello,
And it shows you that you basically have exponential growth in your money.
hello,
Yes.
yeah, that all boss.
Yeah.
Yes, Enoch.
Hi, Enoch.
Yeah, in this limit at n approaches zero, it
And
is
approaches infinity. Yeah. Sorry, I lost you. I think your mic is off. I'm not getting you.
Hello?
Hello, yes. More questions? Rash?
Yeah. That is one of the property, right? We're applying one of the property of the limit, right?
Yeah, I mean, yeah, this is actually how we define the number e is this limit. Right? So this 2.71 is actually usually you define e as this limit. So that's the key thing is that this limit is equal to e.
Okay.
Yeah. All right. Okay. So we have this dE to the RT. So this makes certain computations. And notice, by the way, that this looks a lot like exponential growth, right? We called it CE to the KT, but it's exactly the same thing. We're just using different letters. So this shows that this exponential growth is this amazing thing. It models population and temperature and radioactivity, and it also models compound interest when it's compounded instantaneously, right? Maybe this is worth writing down. So it looks, I'll just say, it looks just like exponential growth. Yes, Rush?
So that is standard limit employing exponential, right?
Exactly.
Like,
Yeah. So let's look at an example. So let's say that we have $1,000 deposited in a bank account paying an interest rate of 5% compounded instantaneously. The question is, how long does it take for the money to double? Okay, so we have our equation, remember. I'm just going to recopy it. Our equation is the amount of money, let's call it y, is equal to dE to the RT. Where here y equals the money in account at time t. Okay, R equals the interest rate. D equals initial deposit. Okay, that's what it all is. So what do we have? In our situation, we have that R is equal to 0.05. Right, R is 0.05. And the initial deposit, D, is $1,000. And so we want to know how long does it take for the money to double? So D is original. So, and what do we know? Well, no, I don't think we even need to say that. Okay. So D is $1,000. And the question is, at what time t does y equal 2,000? Right? That's what we want to know. We start with 1,000. We want to know how long does it take for it to become 2,000? And the answer is we just solve. Same as any other exponential growth, right? So we just have to solve 2,000 equals d e to the r times 2, or 2,000 equals, well, d was 1,000, and r is 0.05. So 0. Oh, sorry. This is not 2. Sorry, this is r times t. So 0.05 times t. Can divide both sides by 1,000. You get that 2 equals e to the 0.05 t. Take ln of both sides. You get that ln of 2 equals 0.05 t. And that tells us that ln of 2 divided by 0.05 is equal to t. And so how long does this give us? It should be about 14 years. So let's see, ln of 2 divided by 0.05. This gives you that t is roughly 13.86 years. Okay, so if at 5% compounded instantaneously, it takes about 13.86 years to double. And notice that that's maybe faster than you would think, because you would normally think, well, every year you get 5%, so to get 100%, which is what you would need to double, that should take 20 years to get 100%. But actually, it's a little faster than 20 years. It's only 13.86 years, and that's because of the way compound interest works. As accounts get higher, the percentages apply, and they get toward doubling faster. And so this applies to a bank account, but it also applies to, national debt at some sort of interest rate, or a business loan, or anything like that. All of these things are done on compound interest that's generally calculated daily, which is effectively the same thing as instantaneously. Okay, so this equation involving exponential growth and decay is really how you can model instantaneously compounded interest. Okay, any questions on this problem?
Hello?
Yes, hello, Rash?
So are we saying that the deposit we are multiplying is double twice?
It will
That I'm
get,
saying.
we're saying that it takes 13.86 years for it to double if you leave it alone.
What I mean, the Y we got, which is 2,000, right?
Mm-hmm.
So are we multiplying the 1,000, or are we just assuming to get 2,000?
Oh, yeah. We're doing 2,000, right? This is the question, right? So you say 1,000 is deposited. How long does it take for the money to double? So we're rephrasing that question as, at what time t is the amount of money equal to 2,000, right? This is exactly it. 2 times 1,000. That's how we get that. Right. That means the money is doubled when it's 2,000.
Okay.
Okay. Okay, other questions? Okay. Yes. Yes, James?
Yeah.
Mm-hmm.
Firstly, you know your rate. Can you know the money you will get based on the time, first deposit, and the rate you are?
Yeah. Sorry, I lost you a little. I wasn't getting you so clearly. It was choppy.
I said that if you haven't, are you getting me right now?
Oh, it's okay. I'll try. Right. So I'm not getting you right now. Okay. So Okay. All right. Maybe I'll answer later. Okay. So, but the point is that this equation gives you, y equals, in this case, 1000 e to the 0.05 t gives you the amount of money after time t. So you can use that to figure out how much is there at any time t. Okay. Okay. Okay, great. All right. So let's okay, so that's it for sequences, and if that's it for exponential growth and decay. I hope you've been convinced in this unit that it's a very useful thing, that it really has lots and lots of applications. Okay, and it all comes down to this basic exponential equation. Can it be used to solve for the initial deposit if the compound interest is given? Yes. Yes. So if you know how much you have at a given time, then yes, you can use that to solve for D. As long as you have all of the other variables, as long as you know the interest rate and you know the time and you know how much money is there, then you can use that to solve for the initial deposit. Absolutely. Okay. Okay. So this is not okay. So we don't have that much time for the new unit, but I do want to start. I do want to talk a little bit about sequences. That will start today. So let me give a quick introduction to sequences. So a sequence, by a sequence, we mean an infinite list of real numbers. Okay. So something like 1, 2, 3, 4, 5, and so on, or 1, 4, 9, 16, 25. These are just the counting numbers. This is the square numbers. And a sequence has to be infinite for our purposes. So if I just write 1, 2, 3, that's not a sequence. Okay. A sequence has to go on forever. And generally, there should be a pattern that tells you how you can compute further entries in a sequence. Okay. Good. Okay. So this is what a sequence is. And generally, how do we use notation for a sequence? We write the entries as A1, A2, A3, and the entire sequence, you can just write it as AN in curly braces, or we can write it as AN if you want to just emphasize that it's an infinite sequence. You can say that it goes from n equals 1 to infinity. By the way, I should give a reference in the textbook for this. So let me remind myself what chapter this is from. This as a textbook reference. This is section 8.1. Okay. Okay. So for instance, you can have a formula for the sequence. So you can think of the sequence given by an equals 1 minus 1 over n. What sequence is this? Well, if we write it out, A1, A2, A3, A4, A5, and so on, well, we calculate each entry in the sequence by just plugging in the correct value of n. So the first entry is 1 minus 1 over 1. That's 0. The second entry is 1 minus 1 over 2. That's 1/2. The third entry is 1 minus 1 over 3. That's 2/3. Then 1 minus 1 over 4, 3/4. 1 minus 1 over 5 is 4/5. And then we could keep going. If you want the sixth entry, that's 1 minus 1 over 6, which is 5/6, and so on. So you can think of this, you could write the sequence by writing down all of these entries and seeing a pattern, or you can give a formula. So in this formula, what we're saying is that the nth entry in the sequence is 1 minus 1 over n. Okay, so I'll just write that. So the nth entry is 1 minus 1 over n. Okay. Is this okay? Kind of what we mean by sequences and what we mean to give a formula for a sequence? Questions? Okay, that's fine. Okay, so we can think of a sequence as a function. So we can actually think of a sequence an as a function from n to r. So I'll write it this way, a function from the natural numbers to the real numbers, where the natural numbers here, this is my domain for the function. And what is it? Well, if I have a sequence A1, A2, A3, A4, and so on, how can I think of the sequence? Well, I can think of this as being, well, what's a function? It's something that accepts an input and gives you an output, right? So it takes an input, which in this case is going to be a natural number, and it gives you an output, which is going to be a real number. So the way we think of this as a function is just f of 1 should be the first entry in the sequence. That's A1. F of 2 should be the second entry in the sequence, A2. F of 3 should be the third entry in the sequence, A3. F of 4 is the fourth entry, and so on. So for example, if I have a sequence that's given by the square numbers, so let's say my sequence is 1, 4, 9, 16, 25, 36, and so on, then we can think of this as a function where we have f of 1 equals 1, f of 2 equals 4, f of 3 equals 9, f of 4 equals 16, and so on. And if we want to write it as a general formula, we could write this as f of n equals n squared. This is the general formula. Okay. All right, so that's okay. So we can just think of a sequence as a function. And for instance, if we have this one over here, we could think of this as being given by the function f of n equals 1 minus 1 over n. Okay, that's just it's the function. It tells you if you input n, the output should be the nth entry in the sequence. Okay, so it's just writing out a bunch of numbers in order. Okay. Okay, great. So let's keep going. Okay, so this is sequences as a function. You can have a general formula here. So there are certain special types of sequences that we're going to look at. So the first type of sequence is called an arithmetic sequence, or this is sometimes also called an arithmetic progression. Okay, so what's an arithmetic sequence? An arithmetic sequence is one where the difference between any two successive entries is constant. And this constant is called the common difference. So we have a sequence like 2, 5, 8, 11, 14, and of course we can keep going 17, 20, 23, 26. The point is that the difference between any two entries here is 3, right? So the common difference in this case is equal to 3. Okay, because each entry is 3 more than the entry before it. Okay, this is called an arithmetic sequence. Okay, something like this, like 1, 1, 4, 9, 16, 25, 36, this is not an arithmetic sequence because the differences between each two successive entries, it changes. To get here, you add 3, but then to get here, you add 5, and then you add 7, and then you add 9, and then you add 11, and so on. So it's not a common difference. Whereas over here, this sequence, everything has a common difference because the difference between any two neighboring entries is always 3. You always add 3 to get from one entry to the next one. Okay, so this is called an arithmetic sequence. And so we can write down a general formula. So if the first entry of a sequence is A and the common difference is D, then how can we write the nth term of a sequence like that? Well, if you start with A, the common difference is D, then the next term is going to be A plus D, then A plus D plus D, then a plus d plus d plus d, and so on. You keep adding a new factor of d, or a new term of d for each entry, right? So in other words, we can write this as a plus d, a plus 2d, a plus 3d, a plus 4d, and so on. And what this tells us is that an, which is equal to the nth term, this is equal to a plus, well, what happens? The second term, we add 1d. The third term, we add 2d. The fourth term, we add 3d. The fifth term, we add 4d. And so the pattern is, for the nth term, we're going to add n minus 1 times d. Okay, so if you have a sequence of this form where the first term is a and the common difference is d, then to make an arithmetic sequence, this is going to be the formula for the nth term. It's going to be a plus n minus 1 times d. Okay, so that's exactly right. So this is exactly what James has in the comments. All right, so in this case, right, we have, a equals 2 and d equals 3. So for example, the eighth term should be 2 plus 8 minus 1 times 3, and this turns out to be 23, which is exactly right, right? I count to the eighth term, 1, 2, 3, 4, 5, 6, 7, 8. It's exactly 23. Okay. That makes sense? Everybody okay with this? Okay. All right, let's move on. So what's a geometric sequence? So a geometric sequence is like an arithmetic sequence, but instead of having the difference between any two successive entries be constant, the ratio between any two successive entries is constant. Okay, and this constant is called the common ratio. So for instance, let's say we do a sequence like 2, 6, 18, 54, 162. If you notice how this sequence, what's the pattern here, is that each entry is 3 times the previous one, right? So we multiply 2 by 3 to get 6, multiply by 3 again to get 18, multiply by 3 again to get 54, multiply by 3 again to get 162. So in this case, the common ratio is equal to 3. This is common ratio instead of a common difference. And so we have the same idea as for an arithmetic sequence. If the first entry of such a sequence is a and the common ratio is r, then how can we write the nth term of the sequence in general? Well, the sequence is going to start out as a, then ar, then you multiply by r again, so you have ar squared, and then by r again, ar cubed, ar to the fourth, and so on. And so what this tells us is that the nth term is equal to, so this an, which is the nth term, is what? Well, the first term is just a, the second term is ar, the third term is ar squared, the fourth term is ar cubed, the fifth term is ar to the fourth. So we see that r gets raised to an exponent that's 1 less than the number of the term, right? The sixth term will be ar to the fifth. The seventh term will be ar to the sixth. So the general formula we have here is a times r to the n minus 1. Okay. So the nth term in a geometric sequence is going to be a times r to the n minus 1. Okay, and we'll compare it to what we had for an arithmetic sequence, which is a plus n minus 1 times the common difference. Here we have a times the common ratio raised to the n minus 1. So this is the formula for the nth term of a geometric sequence. Okay, and so here with this particular sequence, we have a equals 2 and r equals 3. And if we wanted to know the eighth term, that would be 2 times 3 to the 7th. What's 3 to the 7th? This actually turns out to be 3 to the 7th is 2187. So this comes out to be 4374. And that'll be the eighth term of this sequence. So we would have to really count, let's see what happens. 162. Next, you get 486. Keep multiplying by 3. 486 times 3 is 1200, 1440. So it's going to be 1458. And then if you multiply this by 3, you should exactly get 4374. That's going to be the 8th term here. Okay, but you can calculate it by just 2 times 3 to the 7th. Okay. All right, questions on how this works, these geometric sequences? Okay. All right, so you also have general sequences, right? So not every sequence is arithmetic or geometric. There's all sorts of sequences that can happen that are neither. So there's something called the Fibonacci sequence, which is defined as follows. So we start with the first 2 entries being 1, and then for each subsequent entry, we define the entry to be the sum of the previous 2, right? So this says that A3 is equal to A2 plus A1. And then A4 is equal to A3 plus A2. And then A5 is equal to A4 plus A3, and so on. So this is called the Fibonacci sequence. And if you write it down, what do you get? You get 1 and 1 are the first 2. And then each entry is the sum of the preceding 2. So the next entry is 2, because that's 1 plus 1. Then 1 plus 2 is 3. And then 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. And you can keep on adding some more terms. I'll write out a few more. 55, 89, 144, 233, 377. And then maybe I'll stop with 610. But I mean, it goes on forever. Okay. All right. So it turns out the explicit formula for this is much harder. For an is actually quite difficult to come up with. The actual answer is that, and this is going to be kind of crazy, yes, so for the nth element, an is equal to 1 over the square root of 5 times 1 plus square root of 5 over 2 raised to the n minus 1 minus square root of 5 over 2 raised to the n. So it's completely nutty formula, right? But in fact, this is true. So proof is maybe beyond the scope of this course. Proof is beyond the scope of this course, but it is true. Okay, but we don't need an explicit formula because you can get any entry you want by just adding the 2 previous entries. And this is just a sequence. This is not an arithmetic sequence because the sums, the differences between the terms are not constant, right? You're adding 2, then adding 3, then adding 5. So it's not arithmetic. It's not geometric because here you multiply by 1, then you multiply by 2, then you multiply by 3 halves, then you multiply by 5 thirds. It turns out this is almost geometric, that as you get out in the sequence, each subsequent entry is being multiplied by about 1.618 from the previous entries. So it's kind of like becomes close to a geometric sequence, but it's not a geometric sequence. It's just its own sequence. So people have been fascinated by the Fibonacci sequence for a long time. There's lots of stuff to say about it. I'm not going to go too deep into it just because that's not really the topic at hand, but I just wanted to show you as an example, there are these other interesting sequences that are not necessarily arithmetic sequences or geometric sequences. Any questions? Okay. So in calculus, again, you're often going to be talking about limits. So limits of sequences are going to be important for the last thing that we're going to do in class, which is when we're going to talk about what's called a Taylor series or a Maclaurin series. So the limit of a sequence, well, we say that a sequence has a limit L if taking n sufficiently large is enough to get the terms an arbitrarily close to L. And so we write this as our formula. We say that the limit as n approaches infinity of an is equal to L. So it's kind of like taking the limit of a function as n goes to infinity. So let's look at our original sequence, an equals 1 minus 1 over n. This was the sequence that we drew on the first page, 0, 1/2, 2/3, 3/4, 4/5, 5/6, 6/7, 7/8, and so on. And so the question is, what is the limit as n goes to infinity of an? So what does it look like these fractions are approaching? Right? So 1/2, 2/3, 3/4, 4/5, 5/6, 6/7, 7/8. As we go out toward infinity, what are these numbers approaching? And we're almost done. Approaching 1, exactly. Thanks, Armstrong. So, right. This goes to 1 because we see graphically what's going on here. Let's say this is 1 over here, and here's my numbers 1, 2, 3, 4, 5, 6, 7. If I plot the ANs, well, A1 is 0, A2 is 1/2, A3 is 2/3, A4 is 3/4, A5 is 4/5, A6 is 5/6, A7 is 6/7. We see that we've got a horizontal asymptote here, right? And these numbers are approaching 1, okay? And this is, what's the idea here? The idea is that if you take the limit as x goes to infinity as just a function of 1 minus 1 over x, that this is also equal to 1. Because the 1 over x goes to 0, and you're left with just the 1. Okay, so doing a limit of a sequence is more or less the same thing as doing the limit of a function, right? The only difference is that the function, you can plug in all x values, and for the sequence, you're only plugging in natural numbers for the values, right? So I don't draw the graph as a connected thing. I just draw it as a bunch of dots, because in a sequence, we only have n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, 6, 7, so on. All right. Any questions about this? Okay. Okay, great. So last slide before the homework is this general theorem, which is just what I said. Let's say that we have a sequence, and that sequence is actually just the values of a function evaluated at the natural numbers. Then, if the limit of the function is L, then the limit of the sequence is also L. So in our example, if we have that an is equal to 1 minus 1 over n, then I can just take f of x to be 1 minus 1 over x, right? Basically, I just change the n to an x. Okay? And now since we know that the limit as x goes to infinity of 1 minus 1 over x, we know that this limit is equal to 1. What the theorem then tells us, the theorem then says, in fact, that the limit as n goes to infinity of 1 minus 1 over n is also equal to 1. Okay? So it just says that if you can do the limit in terms of functions and you get a value, 1, then the limit of the sequence is the same thing. Okay, it doesn't matter whether you're using x's or n's. So let me actually write one extra little line here. This is equal to the limit as n goes to infinity of an, and this is equal to 1. Okay. So sequences, in order to evaluate sequence limits, it's not that hard. You just do the same thing that you do for a function. You just make believe that it's a function. If it helps you in your mind to change the letter from an n to an x, then that's great. Do that. That can help you understand that it's a function. And then once you have that, then you can just evaluate the limit as if it were a function. Okay, so that's all I want to say about sequences today. The fun really starts next week when we start talking about infinite series, which are more complicated than sequences and give you some nice formulas. Okay, so for homework, just a few basic sequence questions. So these shouldn't be that hard. So number one is if 18, 12, 8 is the beginning of a geometric sequence, write out the next three terms. Problem two is, can a sequence that begins 2, 4, 6 be a geometric sequence? Why or why not? And then problem three is, I'm going to do a sequence, let an be sine of pi n. And what I want you to do is calculate the limit as n goes to infinity of an. And then I want you to notice that the limit as x goes to infinity of sine of pi x actually doesn't exist because the function oscillates, right? So the question is, why is it okay that you have a limit here, but you don't have a limit over here? Why does this not contradict the theorem, over here on the previous slide? Okay, so this question's maybe a little bit more involved. So we'll talk about this in some detail. Okay, but this is going to be the homework, which I'll send out on the chat as always. And so thank you again for your attention. And so next week on May 22nd, we're going to talk about infinite series. Okay, so this is infinite series means you have a sequence, but you're adding everything together instead of just listing it. Okay, any questions? Okay, so if there's no more questions, I'll stop the recording. Last chance to type your name in if you forgot to do it. Okay, so in that case, I'm going to stop the recording.